Hello, everyone at Early Universe from Home in 2026. I'm excited to be here. I'm joining from Karlsruhe. To briefly introduce myself, my name is Kim Berghaus. I do research in theoretical cosmology and particle physics, in particular on the intersection of those two topics. I spent the last 2.5 years as a postdoc at Caltech, and just a couple weeks ago, I moved over to Germany to KIT to start a faculty position. And I've thought about warm inflation ever since my PhD. So on that note, I'm excited to to tell you about the current status and hopefully give you a pedagogical lecture that gets you up to date on the recent exciting developments that have been happening in this field. So let's dive right in. And I will start just saying a couple words about regular inflation, even though I think that most of you already know a lot about it since this is the early universe meeting. But I want to stress a few things, mostly to compare and contrast them to the picture of warm inflation, which I'll get to in a moment. So generally, we we know that general relativity tells us that the content of our universe dictates uh, the rate at which it's expanding. And in particular, to have a period of inflation in the early universe, we need to fulfill a quite exotic condition. We need to have negative pressure. And it turns out, even though this condition seems quite exotic, it's really the simplest field that we can have in quantum field theory that can fulfill this condition. And what do I mean by that? I mean just a scalar field, the first field we learn about in a quantum field theory lecture. And in particular, if the potential energy of that scalar field dominates over its kinetic energy, uh, this scale field system can exactly have negative pressure. And if that makes up the majority of the energy content during a very early period, it can lead to a sustained period of accelerated expansion. So there are a couple things that we need for that. We need that field to be overdamped, such that the kinetic energy is much smaller than the potential energy. And during inflation, we have a quite natural candidate for that damping, and that is damping from the expansion of the universe itself. This is what we call Hubble friction. You can see here, this is a damping term in the equation of motion of the inflaton. And we also need to have a quite sustained period of such accelerated expansion. And this is something that we can see in these so-called slow roll conditions. What I'm showing up here is our potential needs to be quite flat, both in order for it to be overdamped and also in order for it to be overdamped for quite a long amount of time to get the amount of inflation that we need in the early universe. So what's attractive about this setup is that it can not only describe what we're seeing on large scales, for example, in the cosmic microwave background in terms of the um, uniformity of the cosmic microwave background, but it can also explain the small anisotropies that we're seeing. So in particular, in this type of setup, the scalar field has quantum fluctuations, and those quantum fluctuations give rise to small scale anisotropies. So on that note, let's recap very briefly. We have our inflaton field on large scales. It behaves like a classical field, and its equation of motion is described by the damping that it's experiencing due to the expansion of the universe. Now, the fluctuations of that field seed the large scale structure that we're observing in our universe. And there's really only one scale in the problem at the moment, and that really is just the Hubble expansion. So this scale roughly gives us the size of the quantum fluctuations, and it is also the same scale that tells us what the scale of the gravitational waves is. So in particular, the scale fluctuations are characterizing the temperature anisotropies, and then the tensor fluctuations are telling us about the size of the gravitational waves that are being sourced. An important observable in inflation is the so-called tensor to scalar ratio, and in this very simple setup, we only have one dimension full scale in the problem, as we can see, so the ratio between the tensor to scalar ratio is fixed and only depends on the slower parameter. And that leads in this very simple picture that if we ask about constraints on inflation, we see that for the very simplest models, and with very simplest, I mean models with a single parameter that have a monomial potential, such as, for example, a quadratic potential, we generically overpredict the tensor to scalar ratio. So the current state-of-the-art constraints live down here in this blue contour. However, the predictions of these very simple models in cold inflation would have predicted that we should have already seen gravitational waves from inflation, which we haven't. So now let me contrast this very simple heuristic picture with warm inflation. So to be in a picture of warm inflation, let's consider particle interactions. And what exactly I mean by that is something that we will discuss in a lot of detail in this pedagogical lecture. So if we consider particle interactions, we can start living in a different regime. We could be in a universe where during the period of expansion, the space is not only filled by the scalar field, but it is also filled by a radiation bath, by many, many relativistic particles that are efficiently self-interacting, so that they're in a sense of thermal equilibrium and you have a well-defined temperature. In my definition of warm inflation, I'll be using the benchmark where that new scale, that temperature scale, is roughly larger than Hubble, and that's what I mean by warm inflation. So in this setup, the scalar field energy density is still dominating the overall energy density, but now we also have a sizable radiation density such that the temperature can be larger than Hubble. And now you may have already seen that the equations of motion of the inflaton are now also modified. We don't only have Hubble friction that is damping the field. We now also have a thermal friction coefficient that extracts energy from the inflaton field. And you can already see also that the slow roll condition now is also modified, and in particular, in the regime of strong inflation, which is when this ratio here, thermal friction over Hubble, is larger than 1, the slow roll condition is relaxed. It means it's much easier to be slowly rolling a potential if we have another large source of friction. Now, there's another equation that is describing what is happening in this system, and that describes the evolution of the radiation. And you may generically expect that we are in accelerated expansion, and that is shown by the sink term here with Hubble. So any radiation you would expect to dilute. And this is one of the key points in warm inflation. In warm inflation, of course, you have this dilution. This is always there to do due to general relativity, but you're counteracting it because at the same rate at which you're losing radiation to the expansion of the universe, you're sourcing it by extracting energy from the inflaton. And in particular, in warm inflation, you can then reach a steady state, a quasi-steady state system where you maintain roughly a steady temperature. And now what's different about that compared to the previous picture is that the fluctuations of the inflaton are still what seats our large-scale structure, but these fluctuations are now classical in nature rather than quantum, and we have introduced another scale into the problem. Now, these fluctuations no longer only scale with Hubble parametrically, but they also scale with the temperature. And depending on the specific regime of warm inflation that you're in, they can also scale with the ratio of the thermal friction coefficient to Hubble. Now, one thing that becomes very apparent from this heuristic argument is that the condition on the tensor to scalar ratio compared to cold inflation is relaxed. And that is because we have relatively enhanced the scalar fluctuations of the inflaton field due to the temperature. But these temperatures, they're still much below the Planck scale, so we have a very suppressed production of gravitational waves, and in fact Hubble is still the dominant production of them, so we get a large suppression here of the tensor to scalar ratio, which makes it much easier to be within the blue contour that we looked at earlier, which are the stringent constraints that we have today. So there are a couple things qualitatively that I want to emphasize here in comparison with cold inflation. One is because we have this additional source of friction, one can inflate 6D-folds on a much smaller field range. So delta phi doesn't necessarily have to be trans-Planckian. Then, and we already discussed this point, the tensor to scalar ratio is naturally suppressed, which can make it easier to accommodate current observables. And then, and this is just a qualitative difference, it's not necessarily better or worse. In regular inflation, we have, in a way, a two-stage mechanism. We expand, and then the universe reheats after expansion. Versus in warm inflation, in a way, both of these things happen at the same time. And in particular, in the strong regime of warm inflation, there can be just a trade-off towards the end of inflation, where the energy density of the inflaton becomes subdominant to the radiation that it's sourced, and then you're automatically in an FLRW universe that is radiation dominated, so you don't have this separate stage of reheating. You, in a way, expand it and reheat it at the same time. Okay, so all of that sounds interesting, maybe exciting, but the big question, and really, inflation has been proposed over 30 years ago by Arjun Barrera in 1995. So the idea has been around for a long time. But the big open question, really, and I think where really a lot has happened over the last 30 years, is the question on how well motivated of an alternative to cold inflation is this really? And what that comes down to is what type of particle interactions lead to this scenario? Is this a robust prediction of what we would expect from quantum field theory? And this is really the heart of whether warm inflation can be compelling or whether it's a toy model. So let's take a look at that. So let's consider very generically that we want to write down a Lagrangian, and we want to take our inflaton field and we want to couple it to light fields. And here I denoted the light fields to all be contained in this interaction current that I'm keeping very general for now. So what will happen is that we can ask, how does this addition to the Lagrangian affect the equation of motion? And the Lagrangian is linear in phi, so what will show up in the equation of motion is a term that is linear in this interaction current. And in particular, this is the expectation value, the thermal expectation value of this interaction current in the presence of the interactions with the phi field, where the phi field is evolving over time. So now, how can we compute this operator? And this is an operator that we can calculate in thermal field theory, in particular from two-point functions of the particle content in that interaction current. And what we very generically find is that we get a thermal mass correction to the potential of the inflaton field. One very simple way of saying that is you would expect any particle content that lives in this interaction current, let's say, for example, there's scalars in there, you would expect them to get a thermal mass that scales with the temperature squared, and that thermal mass will then appear as part of the potential that now has a vacuum contribution, which was our starting out inflaton potential plus that other term. And then, as a subleading term, we would also expect to get this dissipative term that we relied upon to extract energy density from the inflaton. And this is an argument that I will go into a little bit more detail in just a second. But a big crux of the issue here is that it appears that the leading order term is this thermal mass correction. And the term that we actually needed/wanted for warm inflation is the subleading correction. So this led to the question posed in 1998 by a paper by Yokoyama and Linde with the title, "Is warm inflation possible?" And what that paper pointed out is that in a way, both the dissipative effect and the thermal mass corrections are two sides of the same coin, and usually one is much larger than the other. And that spoils your ability to be in this scenario that I just described. So let's zoom into that in a little bit more detail. Okay, so let's take a look at our timeline. So in 1995, warm inflation was proposed. And then in just 1 second, then we had, is warm inflation possible? Yokoyama and Linde. That was in 1998. And I want to sketch the argument in a little bit more detail. So let's consider a very simple example term. Let's consider a Lagrangian where we have the following coupling, where phi is our inflaton field, and we're coupling two chi fields. And then you can already see from this that you could write this. You can write this as such a term. So you see very naturally that you get a thermal mass here, where our thermal mass is just given by the thermal expectation value of our field. Okay, but we know what the thermal expectation value is. We can calculate it. And in fact, the leading order term just scales with the temperature. So notice that we don't have any phi dependence here, but we get a correction. Okay. So what is the leading term? Only scales with the temperature. There's no phi dependence here. So you may ask, how do we get this dissipative dependence? How do we get a term that scales with phi dot? And you can, but what you also see here is that the subleading correction to the thermal mass depends on phi. And phi is in fact changing. And due to that change, we're introducing a drag. So this second order term is obtaining another correction. And in a way, the dissipative term that we get, the term that we need for warm inflation, that dissipative friction term arises as a correction due to the phi dependence here, heuristically. So what that shows you in this very simple example is that here the leading order term just scales with the temperature. The subleading correction to the thermal mass has some phi dependence, and then the correction to that gives you the dissipation. So as a consequence of that, generically, when you have a simple coupling like that to a scalar field or fermions, you get this hierarchy, because this just arises due to a correction of a correction. And this argument is easiest to see with this type of coupling, because you can very easily write down what the thermal mass is. But in fact, and this is what Linde also did, it also holds up if you consider slightly different terms, something like this, or even if you consider something where you try to get a cancellation for the mass, you still always end up with a similar problem, and you can calculate this more rigorously in thermal field theory as well. So now, where does it lead us? So I want to tell you historically what happened next. And yeah, I want to briefly say I've spoken with a lot of people, and there's been quite a lot of skepticism if warm inflation can work or how compelling it can be. And a lot of people refer back to this paper and the arguments in this paper. So I want to highlight that really a lot of progress has happened since then, and I want to briefly sketch out kind of the order of those things. So here we're at 1995 and then 1998. So let's so we have a first existence proof of a model by Barrera in and that was in 1999. And in that existence proof, there that relied on couplings that looked like this. But this by itself doesn't work, as the Linde paper shows in detail, and you can review it there if you're interested in the details. So what needed to happen here was that there needed to be a tower of particles where basically, as the field was rolling down, constantly new particles would get into a band where they would be light enough to be excitable without having a large back reaction. So this required a huge tower of particles. So here we were talking of order 10 to the 4 fields. So one could maybe argue that while this is an existence proof, that within a quantum field theory, you can avoid this hierarchical argument that you always mess up the flatness of your potential with your thermal mass correction. But you could argue that maybe needing 10 to the 4 fields is not particularly compelling, so you don't want to put it on equal footing to the cold inflation alternative. So that was in 1999. Then we had another idea in 2006, and that is the idea of using heavy mediator fields. That was by Moss and Zing in 2006. So here the idea is if your infiltron directly couples to a heavy field, you don't get a thermal mass from that because there's no thermal bath of these heavy particles, but these heavy particles can still virtually mediate interaction with lighter fields. Naturally, this is going to be very suppressed because we have the heavy mediator fields suppressing all dissipative effects, but you can still um, get dissipation. So what you needed here was still order 10 to the 3 fields. So still quite some complexity. So some of you may already be thinking, okay, what is one of our favorite tools in quantum field theory? Those are symmetries because they suppress maybe or don't allow for terms that we may not want to appear in our theory. So this is what happens. This is a big jump that has happened after this, and this is recognizing that symmetries are useful. And in fact, all other solutions I will talk about will exploit these ideas. In particular, in 2016, there was the proposal of the worm little inflaton by Bastero, Gil, Barrera, Ramos, and Rosa. And here, now we've greatly reduced the number of fields. We only need 4 fields. Here, the idea is to make the infiltron field a pseudo-Goldstone boson that's protected by broken U1 symmetry. And due to that symmetry, they claim that you end up having an exact cancellation with the thermal masses, but not a cancellation, the dissipation, due to it being a non-local effect. So here we see that there was a great reduction in complexity already. And then what happened afterwards, what I worked on in my PhD, is the idea of minimal warm inflation. We had left off at minimal warm inflation. That happened in 2019. This is what I worked on in my PhD. And there you would, in a minimal setup, you would need 3 fields. And there the idea is if your infiltron is an axion-like coupling and you couple to a non-abelian gauge group, and that SUN, if that N is 2, you would introduce 3 new fields. So this already is quite minimal, but of course we don't have a pure SUN in the standard model. But now what has happened very recently, and this here was with my co-authors, Peter Graham and David Kaplan. And then what has happened very recently in the last year is worm inflation with the standard model. And since I haven't been counting the inflaton as a new field here, I guess that would lead to 0 new fields required. And here, the GG dual that you couple is the GG dual of QCD. And I worked on this with my co-authors, Marco Dreves and Sebastian Zell. So if we take a look back at this timeline, starting all the way up here, the idea was proposed over 30 years ago. Quickly, it was questioned whether it was viable at all. But slowly, model space has been discovered that has shown that this is not only viable, but in fact quite minimal, leading us to today, realizing that actually just taking inflaton field and allowing it to couple to the QCD field strength can give rise to this compelling setup of warm inflation. So as you can see, there's been a lot of progress, and it has really gone from can this happen at all, to this is actually extremely generic to happen, since we know that QCD exists in nature, and if there was an inflaton field, it may not seem far-fetched that it would couple to the forces in nature that we know exist. So now I want to tell you a little bit more about the theory that goes into particularly the last two ideas, particularly setting it up with the standard model. And then I'll say a couple more general words about the status of calculations and observables and warm inflation. Okay, let's switch back over. Okay, this is where we left off. Okay, so what's going on with the setup of minimal warm inflation? So what's compelling about coupling to GG dual? And for context, we're here at a temperature where we're above the confining scale of the temperature. So in this model, it's the gauge bosons of the non-abelian gauge group that comprise the radiation. What's happening here is that when we calculate the expectation value of this operator, it's precisely the thermal mass back reaction that's not allowed by symmetry. In a way, it's very similar to another example that was mentioned, and we know that an axion, we can think about it as a pseudo Goldstone boson of a broken symmetry, and as such, it's protected by its symmetry from such a thermal mass. But this coupling is also unique not only because of the protection of the symmetry, which you could also imagine in other theories. It's unique because the particle protection itself actually gets an enhancement from a non-perturbative phenomenon. In particular, there are sphalerons that are present in non-abelian gauge theories that give an enhancement to the extraction of energy from the inflaton field. So this is quite a unique phenomenon in that sense. So let's talk for a moment about sphalerons. So sphalerons were discovered in 1984 by Franz Klinkhammer and Nicholas Manton. And I had the pleasure of meeting Nicholas Manton in person in Cambridge earlier last year. And he was so kind to share with me a snippet of the original exchange that they had with the referee back. And I'll give you a moment to look at their exchange. So what you can see here already is that there was some pushback to using the word sphaleron, even though, but clearly they won, since now it is a well-established terminology in quantum field theory. But let me say a couple words about sphalerons. In non-abelian gauge theories, you can not go continuously from between a vacua with different winding numbers. You need to go through a large gauge transformation. So in a way, there's a finite barrier that can be overcome, and that can be overcome classically or through tunneling. When we talk about tunneling, we usually talk about instanton effects, but the classical configuration on top of going from one winding number to another one, those are these Faleron solutions. So what you could think of is that you have gauge fields, and to go from one to the other, you would need to have a gauge field configuration with finite energy in it, and then from there it can decay into a vacuum with a different winding number. And these winding numbers, we call them Chern-Simons number. And what happens at high temperature is that these barriers are very highly suppressed, precisely because classically you have enough energy to go from one vacuum with one winding number to another. So this coupling that we write down is phi to GG dual. We can integrate it by parts, and at the homogeneous level, we can write it as the phi dot term, the finite speed of the inflaton field, giving a chemical potential to the Chern-Simons number, which is the winding number. In a way, the inflaton acts as a chemical potential. And what I've indicated here in this figure, and what I'm showing here, and this is not the inflaton field. This is the vacuum that we're moving in. The inflaton field drives transitions to different vacua, and the the little bumps here are still exaggerated. At high temperature, they're really highly suppressed. But what happens is, as we go from one vacuum to the other, we kind of go through these Fallon configurations, and they decay and produce particles. And the particles that they're producing are gauge fields. We very clearly have a bias, so we keep driving these transitions, which leads to ongoing particle production. And this is what enhances the injection of energy through this coupling. So and now we can relate what the rate is of that energy injection to this Fallon rate. We know how this Fallon rate scales, and using the so-called fluctuation dissipation theorem, we can derive what we think the dissipation is that arises from this Fallon friction. So precisely the friction coefficient, the thermal friction that we are interested in the context of warm inflation, precisely that quantity we can relate to the quantity in our theory, which is basically alpha, which is our coupling, and then the color of our group, and the temperature and the scale F, which is also here a part of the coupling. So now this is the idea of minimal warm inflation, but of course now what happens if we want to couple to QCD? Because ultimately we are interested not in a pure SUN, but in the gauge groups that we know exist in nature. What happens now once we have quarks in the system is very interesting, because that impacts the dynamics. And in particular, when we have quarks in the system, every time we go to a different vacuum, we actually have a change. We're building up more left-handed quarks than right-handed quarks. And this is exactly what these sphalorants do if they are going through a bias transition. What happens is that heuristically, and you can show this here, you can see this here in the image shown at the bottom. What that effect leads to is building up an opposite chemical potential to the inflaton. So each time we go through a transition, we're putting in more left-handed particles. And eventually you would expect that they're exactly counteracting each other out. And then you may think that for QCD, you don't have a sustained thermal friction that allows you to be in warm inflation. And in fact, when I was first working on this, we had just started to understand what would happen when you take fermions into account. And this was a big worry that you have a large back reaction there. So now what we realized in very, very recent work, the one that I put out with collaborators last year, is that actually Hubble dilution enables warm inflation with the standard model. The idea is actually extremely simple. While you're building up this counterweight, at a very constant rate, you're diluting this chiral quark charge that you're building up. So even though you keep producing left-handed particles, just by the universe itself expanding, you're shrinking this counterweight. And this is a feature of inflation that you can't turn off. We know that Hubble is there, so this dilution is always there. And what that actually leads to, if you're asking how effective is the particle production, is that you can be in different regimes. You can be on one hand in the regime where the quarks don't back react at all, because you're diluting so effectively that you're still producing at the same rate as you did for the pure SUN expectation. And then there's this opposite limit where you're limited by your rate of dilution, and that would be the limit where the second term here, highlighted in green, is dominating. So now, where does it lead us? Where this leads us is that we now know that even if we couple directly to QCD, we have different regimes in which we have effective particle production. And in fact, we understand that particle production very, very well. And what's also quite interesting about this equation here is that there are different limiting cases. So in this case where the white term here dominates, we just get the regular cubic dissipation, which we've seen previously. But if this term here dominates, then we actually, these two terms cancel, and we get quadratic dissipation. And in none of the other models that I described previously, there has been a microphysical example where you can get quadratic dissipation. So this is a proof of principle that within this theory, there are regimes where you macroscopically behave like that. And in particular, as you go to transition regions, you can also end up with dissipation coefficients that are fractional, that effectively have a fractional temperature dependence. Something, if you're going between t squared to t cubed, you can have regimes in your theory that look like 2.5 or so. Okay, so what this shows is that we do have parameter space for QCD where we get effective dissipation and particle production. Now, going back to the plot that I showed before, where we were plotting the tensor to scalar ratio as a function of the spectral index, on the left, I'm showing here the constraints, and this contour in blue here is the same one that is shown here in gray. And for warm inflation with the standard model, we're showing the data points right here. And what's different compared to the cold example is in warm inflation we don't have an uncertainty in the amount of e-folds. Because we can have a smooth transition into a radiation dominated period. So that's why we don't have a band here, like with the red curve. We just have stars, and the number here tells you what the amount of e-folds is that you needed to reproduce the cosmic microwave background. So now, what is it that that went into this theory? The ingredients are really very minimal. On one hand, you have your inflaton with a potential, and here we chose a quartic potential, mainly motivated by it phenomenologically fitting the observables very well. And the only other thing that you add to it is a coupling to QCD. So you have, and we know what alpha is in QCD. It's a strong coupling, and we know how it runs in the standard model at high temperature. So then the only other unknown quantity is the coupling strength F. And your observables fix a linear combination of lambda and F. So then you have one free parameter that basically takes you along this curve, and it parameterizes how large the ratio is of the thermal friction to Hubble. So down here, with very suppressed tensor to scalar ratios, it's quite large. And up here, it's quite small. And in particular, what I'm showing here is only the regime in which the back reaction from the chiral quarks is small. So for order 30ish or so of this ratio, you don't have a sizable back reactions of chiral quark production onto your dissipation coefficient in warm inflation. And if you go further down, that back reaction actually becomes large. So now this result has actually received quite a lot of attention in the popular media. It was highlighted by Nature Research Highlights. And it was also featured by Scientific American. I personally think it's a quite an exciting result that we can have warm inflation literally by just taking the inflaton field and considering coupling to QCD. Now, zooming back out on a more general note, what is the status of warm inflation observables beyond any one specific model? What I've had people comment to me is that they find the warm inflation literature confusing or difficult to follow, or that there are some internal discrepancies. So I want to briefly comment on the status of calculations. So one very important prediction for observables is, of course, the power spectrum, and really what I want to briefly say as a big picture, I think actually that at this point, the majority of any discrepancies have been resolved, and there's actually quite a lot of consensus, and especially there's also been a clear trend of improvement. So taking, for example, the power spectrum, there are very earlier works here. In the earliest work, a term was missing that was then pointed out in subsequent work. And now, more recently, partly motivated by the very simple models that give rise to warm inflation. Some of these calculations have been revisited in different frameworks. So the early universe all used a fluid approach. More recently, Mir Babaji and Gruzinov used an effective field theory framework to revisit some of these calculations, and actually overall found decent agreement with what has been done before. In some instances here with the power spectrum, they pointed out one additional term that was neglected that led to very small discrepancies. And then excitingly, in more recent work by Mikko Lane and collaborators, they did a more fundamental calculation starting from thermal field theory, and actually found also quite good agreement for large parts of the regime with the EFT approach by Mir Babaji and Gruzinov. So I would say we now have really two different approaches that agree quite well with one another. On the numerical code side, there have been two code packages. One more recent one, the one from Ramos, for example, has also picked up the extra term that was pointed out that led to very small discrepancies here, and that is fully included here in their numerical code base. There's also been a previous Python-based code that was implementing the previous calculations here from the earlier work. So I would say on the power spectrum side, they're beyond very, very minor arguments. There really is quite a lot of agreement and a lot of robust theoretical development and framework behind what the predictions are telling us. So I think it's really quite reliable. Then on non-Gaussianities, there were also earlier works that made some predictions, and in particular, what these earlier works pointed out by Bastera, Gil, Barrera, Ramos et al., is that in warm inflation, you would expect a unique bispectral shape that is distinct what you would basically expect from shapes in cold inflation. And in a recent updated calculation by Mir Babaji and Gruzinov, they reaffirmed that expectation. They also found that there is a unique bispectral shape, even though their bispectral shape showed some minor differences, and there were also some differences in the predicted amplitude of the non-Gaussianity. In particular, the more recent work predicted a larger amplitude, which potentially could be exciting and trying to look for it and discover it. But yeah, I mean, there's yeah, would certainly be interesting to see if other groups would agree with this result to have yeah, several groups agreeing as is happening with the power spectrum results. And then on the sides of gravitational waves, there has also been work, and my list is in no means exhaustive. I'm just highlighting some works that I particularly found very interesting. So there's very robust work from several groups going into refining these observables and putting them on very solid footing theoretically from different perspectives. So with that, I wanted to very briefly leave you with that potentially warm inflation combines the strong force with the unknown physics of the very early universe, cosmic inflation, in particular, maybe via this axion-like coupling, a Lagrangian that is of much interest, not only in the context of inflation, but also in terms of many topics in beyond standard model physics. So what I want to leave you is what I think we're all curious about investigating are like, what are the laws of nature that govern the evolution of our universe? And it seems like this Lagrangian, this axion-like coupling to GG-DO QCD may be at the center of many of the ongoing puzzles, such as heating the early universe, the nature of the inflaton, solution to the strong CP problem, and the nature of dark matter. So there may be very many interesting connections between warm inflation and these questions. And with that, I'll hope to see you in the discussion session.